So this isn't your average chemistry or physics lab. TRIUMF is a particle accelerator like CERN that you might have heard of in Switzerland, but different in scale. The particle accelerator at CERN has a circumference of 27 kilometers. We're a lot smaller. So we've got the linear accelerator, accelerating the H-, depositing it in the center, and then spiraling outwards as it gains energy until they get extracted down the multiple beam lines that we have. We don't produce the same type of particles that CERN does. They're looking for the Higgs boson and high energy particle physics. We're producing muons and radioactive ions, and our focus is on condensed matter physics and chemistry, not on particle physics.
Any beamline facility, any particle accelerator facility, like, they always impress me with how much equipment's involved, the resources that are needed, the amount of money that goes into it, the number of people involved. It's just all that. It's something that I think really it does leave a lasting impression on you.
So I'm a research scientist at TRIUMF, and I have two roles. One of them is assisting scientists who come here to do experiments with their research. Often they don't have the expertise in this technique that they need to perform these experiments, and that's where I fit in. The other is to advance my own research. My research bridges physics and chemistry. So I want to understand how things behave at the molecular level. And if we can understand that, then we can design new materials that have better properties. So a muon is a subatomic particle. It's radioactive, so it has a lifetime of 2.2 microseconds. We implant these muons into a material, and they act like little bar magnets inside it. They're measuring what the local magnetic field is inside the material and how that magnetic field may be fluctuating around. And that tells us something about what's happening inside the material at the molecular level. So the way the experiment works is that we have a beam that gets implanted into a material, and the material is put in the center of the spectrometer. And the spectrometer has radiation detectors surrounding the sample, and so it measures the radiation that comes off it, and then that's what provides us the information about the microscopic behavior. We apply them to a whole range of problems. So example, I'm doing experiments right now on battery materials, understanding how lithium ions move through those.
My research project consists of studying lithium-ion mobility in materials that are important for lithium-ion batteries. So these are batteries that are contained, for example, in your mobile phone. This could be something also that you'd find in a laptop. Nowadays, more recently, something that you might find in a vehicle. The important thing here is that we want to study how fast the lithium ions move, because this directly affects how fast they are charged and discharged. If we understand that better, we can design materials that are used in such batteries. So the way we do this, the way we perform this experiment, is we make use of a lithium-ion beam. This is something like 10 million lithium ions per second that are implanted into a material of interest. The typical size of that beam that we work with is on the order of 2 to 3 millimeters, so extremely small, and overlapped on a sample that is usually 8 to 10 millimeters, give or take. It's implanted, it finds itself into a metastable site, which means that it settles into its resonance site, its most friendly spot to be at, that's energetically preferable. And then it hops between sites. When it does this, that is something that we can actually detect with our measurement technique. Anytime we collect data from the experiments, from our spectrometer, we have a raw output that needs to be fit to a model in order to make sense of it, in order to actually connect it to the phenomena of interest that we're actually after. The model is usually based out of something from, say, a physical theory. Creativity is important in really any research, to my mind, because in order to conceive of and to design an experiment, you have to have a creative mind, I think. You have to be able to come up with different ways to approach a problem that someone has never thought of before, because at the end of the day, any scientific research is attempting to resolve an unresolved research question up to that point. So in order to really do that, you have to have a creative mind. You have to be able to think outside the box.
There's no such thing as a typical day here. When we're running experiments, they go 24 hours a day for sometimes several weeks at a time. And on those days, it's go, go, go.
Every research group here at the Isotope Separator and Accelerator, which is the facility that we're currently at, which is a subset of TRIUMF, every research group has only a select amount of time per year to make use of. In our case, it's about 4 weeks of total time per year. This is distributed amongst myself and all of my other close collaborators. So the rest of the time that is not devoted directly to the experiments that take place here, so this is the 48 or 47 other weeks of the year. This consists of writing papers, collaborating with other experimenters. A lot of analysis takes place to understand the data that we just collected.
So we're in the ISAC radioactive isotope beam control room, and this is where operators work to transport the beam to the experimental area. There's staff here 24 hours a day, 7 days a week. Most of the operators who work here have training in physics or chemistry, and they're monitoring various equipment through the beam lines, so looking at rates on various detectors, and optimizing the beam transport to our experimental area.
With a facility as large as this and as extensive as this, you cannot be an expert in everything that takes place here. So for example, like our own spectrometer has a resident expert who is responsible for its maintenance, its development over many years, but that is really the kind of endpoint, and everything that goes up to that point, like everything that is, shall we say, upstream of that, requires experts from a variety of different fields. We have to be involved with dozens, sometimes even hundreds of other people. So the collaboration is absolutely essential. We have to be able to talk back and forth in order to really ensure that these experiments run smoothly.
At TRIUMF, we produce radioactive particles, and so there is radiation around. And safety is our number one priority. And so we have various forms of detectors to probe radiation. So I'm holding up 2 dosimeters here.
The concrete blocks provide shielding for radiation that is produced when, for example, the protons interact and bombard a production target. When that happens, an enormous amount of radiation is produced. So you have to shield that in some way. So the concrete blocks provide that shielding.
Reproducibility is incredibly important in science. That's why we publish our data. That gives people a chance to look at it and reproduce it for themselves. But we take this a step further. We actually display all the data that is taken here, and it's searchable by anyone online. Reproducibility is more important when you have unusual results. So we don't tend to reproduce things that act as expected. It's only when you get new physical behavior that you go, did I do that right? Then we'll try and reproduce it and see, yes, that actually is really how the system behaves. And it's those sort of head-scratching moments that actually turn into new discoveries. Failure gives you a reason to investigate something more carefully. If everything worked out, I think we'd probably just have a much more superficial understanding of things.
The role of ethics in, say, the field of a physicist or a chemist is going to be quite different from what you might encounter for, like, say, someone who works in the medical field, where you have very stringent ethical concerns, especially if you're involving, human clinical trials or something like that. But in our case, because the resources that we require are so intensive and so costly, we have to be very judicious and responsible as to how we make use of the experimental facilities here. So, we cannot waste any time. We have to be very, very mindful of the cost overall.
One of the ethical considerations with working here is balancing the resources that are used to run TRIUMF, which can be millions of dollars a year in terms of electricity costs, and that's contributing to climate change. Balancing that with the societal benefits that can be produced here, like designing new battery materials that will offset the cost of the research.
I think as you pursue the sciences in the real world and you become a researcher, you start to become comfortable and content with not knowing. You become really, familiar with the unknown. It's really a transformative experience, and it's, I would have to say, a lot of fun to become one with the unknown, so to speak.
Science is exciting. And I don't think that excitement is really conveyed in popular culture. There is nothing as thrilling as making a discovery and understanding how the universe works just a little bit better. It's these dopamine hits of discovery that really motivate me and keep me doing this over and over.